In this video, we will solve a variety of problems using the second fundamental theorem of calculus, which tells us what happens when we take the derivative of something called an integral defined function, which is what this is. An integral defined function is a function that involves an integral. The first time I saw one of these, I found it very confusing that there were two different variables that you could see. There was an x and there was a t. What's going on here? Well, the real variable is the one that you find where you would expect to see a limit of integration. So the real variable is the x. That's why you see this is g of x. The t is really just a placeholder. And you'll see when I do this quick example, the t disappears. So the t doesn't really matter. We're just calling it something other than x so we don't get confused between the x and the t. This integral defined function is just a function like the ones you've been working with for years. You have an input and then there will be an output. So if I want to find the value of g at 3, I simply substitute the 3 for the x and I do the calculation. So in this case, substituting 3 for x provides the upper limit of integration. So I am evaluating the integral from 2 to 3 now of 3t squared dt. In order to do this, we need to integrate 3t squared. I'm going to use the power rule of integration. So I'm going to have the t, I increase the exponent by 1, that's t to the third power, and then I divide by my new exponent. But if I divide by 3, that cancels out the 3. So I get t to the third power. Then I reapply my limits of integration, so that's going to be from 2 to 3. And this tells me I need to find the value at 3 minus the value at 2. So here's the value at 3 minus the value at 2. In this case, we have 27 minus 8, which is 19. So just like any regular function, you have an input and an output. G at 3 turns out to be 19. The second fundamental theorem of calculus tells us what happens to an integral defined function when we take the derivative. The second fundamental theorem of calculus has a general case and a common case. We're going to start with a common case. This is the one where we have a number for the lower limit of integration, just a constant, and a simple variable, just x, for the upper limit of integration. The common case says if you take the derivative of this function, the derivative and the integral basically cancel each other out, and you end up with f of x. So the placeholder variable turns into the real variable. Here is another way of expressing the same thing. If capital F of x is equal to this integral defined function, then capital F prime of x, the derivative, will equal f of x. For the next few problems, we are asked to find the first and second derivatives given an integral defined function. According to the second fundamental theorem of calculus, common case, if we take the derivative of an integral defined function, the integral goes away and we are left with the function that's on the inside, but the placeholder variable becomes the real variable. So f prime of x, capital F prime of x, should equal sine of 5x. Please note that this derivative can also be called f of x. So we could say f of x equals sine of 5x. So that's the first derivative. Now let's go ahead and find the second derivative, which will just be the derivative of the derivative. So the derivative of sine 5x is cosine 5x. But because of the chain rule, I need to multiply by 5, which I think I will put in the front. So this is the second derivative. Notice that this second derivative can also be called f prime. Before we move on, I want to say a couple words about the relationship between this capital F and f of x and f prime of x. Let's start with what we are familiar with. If we have some original function f of x, if we take the derivative of that, you know we're going to get f prime of x. And then if we take the derivative of that, we're going to, of course, get f double prime of x. So here's where the capital F comes in. The capital F is the antiderivative of f of x. In other words, it's what comes one step before f of x in this chain. That's why if I take the derivative of capital F of x, I get f of x. That's what I'm expressing up here. And if I do the second derivative, that means I'm taking the derivative once, that gives me f of x, and I take the derivative again, that gives me f prime. So that's why capital F double prime is equal to f prime. So if you keep this sort of chain in mind, all the way back to capital F of x, the antiderivative of f, it will help you understand the relationships between all four. Problem number 2. This is still the common case. We have the constant as the lower limit of integration and then x as the upper limit. So according to the common case, the derivative should just be the inner function with the real variable x instead of the placeholder. Again, note that this derivative is g of x. Anyway, now we need to find the second derivative, so g double prime, which will be g prime. So I just need to take the derivative of this. We know that the derivative of e to the something is e to the something. However, we have to do the chain rule. So this is x to the 1/2 power. So when I do the chain rule, I'm going to have times 1/2 x to the negative 1/2 power. So we can simplify this a little bit. Here's your 1/2, kind of big. And the e to the radical x power will be in the numerator. And then this x to the negative 1/2 power is going to drop down to the denominator as a radical x. And in that case, we don't need the 1. For number 3, this is almost the common case, except it is backwards. Instead of having 3 to x, we have x to 3. Here is a step that you don't need to show. I'm just reminding you that if you reverse the limits of integration, it changes the sign. So now we can go ahead and find that first derivative. So capital H prime of x, which equals h of x, will be, let's see, the negative sign will stay there. The derivative cancels out the integral, and we are left with the inner function. So natural log of x squared plus 2. The second derivative will equal h prime. So we just need to find the derivative of this. The negative sign remains. We know the derivative of natural log u is 1 over u times u prime. Got to do the chain rule. So I am multiplying by 2x, but I will put this in the numerator. So there you go. Number 4 is not the common case because we don't just have an x, we have x squared. So I need to tell you about the general case. We need to use the general form of the second fundamental theorem of calculus when we have a function either for the lower limit of integration or the upper limit of integration, or both. According to the general form, if we take the derivative of this, first you plug in the upper function, so I will have f at v, but then you multiply by the derivative of v. Then you subtract, and you plug in the lower function. So I subtract f at u times u prime. So let's give it a shot. I want to find the first derivative, which will equal j of x. And according to the general form, first I plug in the upper function. So that will be arctangent of x squared. But then, similar to the chain rule, I multiply by the derivative of x squared. So I'm going to multiply by 2x, which I think I will put in the front. So there's my first derivative. Now for the second derivative, which will equal j prime. I need to take the derivative of what we see. This will, of course, be the product rule. So I'm looking at this as the 2x and then times the arctangent of x squared. So here's my product rule. I will first take the derivative of 2x, which is 2. And at this moment, I leave the arctangent x squared alone. And then I put a plus, and the second time through, I leave the 2x alone. And then I multiply by the derivative of arctangent x squared. But remember the rule. The derivative of arctangent u is 1 over 1 plus u squared, of course, times u prime, the chain rule. So here we go, 1 over 1 plus u squared. So that's going to be x squared squared. Don't forget the chain rule. We need to multiply by the derivative of x squared. So that'll be 2x. And we can simplify this a little bit. We can multiply the 2x times the 2x, and we get 4x squared. And x squared squared is x to the 4th power. So here you go. For the next two problems, we are asked to find the equation of the tangent line for an integral defined function. This will work just like it did first semester with a regular function. Whenever they ask us to find the equation of a tangent line, we like to use point-slope form, which looks like this. This reminds us that all we need is a point and the slope. Let's start with the point. They gave us the x-coordinate of the point of tangency, so we just need to plug it back into the original function to find the y value that goes with it. So we need to evaluate capital F at pi over 4. That means we will substitute pi over 4 for the upper limit of integration. We can integrate this using our derivative rules. Ask yourself, the derivative of what will give you secant t tangent t? The derivative of secant t will give you secant tangent. So this is the integral, but don't forget this is a definite integral, so we need to evaluate this from 0 to pi over 4. This means that we need to find the value at pi over 4 and then subtract the value at 0. In other words, secant pi over 4 minus secant 0. Remember that secant is the reciprocal of cosine. So cosine of pi over 4 is 1 over radical 2. So secant will be radical 2. The cosine of 0 is 1. So the secant will also be 1 because the reciprocal of 1 is 1. So this is the y value that goes with this x value. In other words, we now have the point, which is pi over 4, comma, radical 2 minus 1. So we found the point. Now let's go back and find the slope. So in order to find the slope, of course, we will find the derivative. So we need to find capital F prime, which will equal f of x, by the way. This is the common case with a constant for the lower limit and x for the upper limit. So we can simply write the inner function down with the real variable instead of the placeholder. So I will write secant x tangent x. And that's it. This is the derivative. So we need to evaluate this at pi over 4 to find the slope. So we need to do secant pi over 4 times tangent pi over 4. Since cosine pi over 4 is 1 over radical 2, I know secant pi over 4 will be radical 2. And tangent pi over 4 is 1. So that means that the slope is radical 2. So now we have a point and the slope. The equation of the tangent line will be y minus y. So y minus all of this. When you have a binomial, you need to put it in parentheses. So I need to do y minus radical 2 minus 1 is equal to the slope times x minus the x value of pi over 4. There it is. For number 6, we are once again finding the equation of the tangent line to an integral defined function. So let's go ahead and find the point. We need to plug the x value into the original function to find the y value that goes with it. So we need to evaluate g at pi over 2. So that means we need to find sine of pi over 2. Maybe I'll do this in 2 steps. So if I plug in pi over 2 for x, that means I have sine of pi over 2 at the upper limit of integration. But we know that sine of pi over 2 is 1. So just keep that in the back of your mind for the next step. So this is really just a 1. Anyway, let's continue. So we have e to the 2t dt. So we need to integrate. I am doing a mental u substitution right now because the integral of e to the u is e to the u. All right, the 2t is my u. But what would u prime be? U prime would be 2. So when u prime is a constant, you end up dividing by that. So that's why I'm going to put a 1/2 in the front. And instead of putting the plus c that we would often put, I will put a vertical line showing my limits of integration. So from 0 to 1. So this tells me that I need to find the value at 1 and subtract the value at 0. So here is the value at 1 minus the value at 0. Well, this is really 1/2 e squared. E to the 0 power is 1. So this will just be minus 1/2. I could factor out the 1/2 to clean it up a little bit. So we have 1/2 times e squared minus 1. Remember, all of this is the y value. So we now have the point. It's pretty crazy looking, but it's still just a point. The x value is pi over 2, and the y value is all of this. So 1/2 e squared minus 1. Okay, that's the point. Now we need to find the slope. So let's get ready to find the derivative of capital G, which would be the same as g of x, by the way. Notice that this is not the common case, so we have to be very careful. So when we do the general form, we take the upper function and we plug it in. So I'm plugging it in for t right here. So that gives me e to the 2 times sine x power. But we immediately must multiply by the derivative of the upper function. So the derivative of sine is cosine, so I need to multiply by cosine x. And then we are to subtract, and we plug in the lower limit of integration, which in this case is just 0. But if I plug that in, I'm going to get e to the 2 times 0. But then I need to multiply by the derivative of this lower limit. And the derivative of 0 is 0. So really, the second part is gone. All right, this is all just 0. So my expression for the derivative is just this. Now we need to evaluate the derivative at pi over 2. So we need to do capital G prime at pi over 2. So that will equal e to the 2 times sine of pi over 2 times the cosine of pi over 2. But check this out. Sine of pi over 2 is 1. So fine, we have 2 times 1, which is just 2. However, cosine of pi over 2 is 0. So that's going to wipe this out, and the whole derivative, the slope, is 0. The easiest thing to do is to recognize that because the slope is 0, that means we have a horizontal line. And a horizontal line will always be y equals a number, which in this case will just be the y value that we found. So y equals 1/2 times e squared minus 1. And that is the equation of the tangent line. Or you could stick with point slope form and do y minus y is equal to the slope times x minus x.